Okay, which one has a greater rotational speed? Notice I gave you an equation and some possible units. Thumbs up when you have a guess. Have a conversation. Okay, what do you say? All right, so rotational speed has units of rotations per second, revolutions per second, sometimes RPM, heard of that? Rotations per minute, okay? Degrees per second, radians per second. It's how quickly you're doing 360 degrees. Which ball is doing 360 degrees or a rotation in the least amount of time? The same, right? They tie. Okay, so they both have the same rotational speed. That's not zero. D, dangerous dinosaurs. Good with that? Okay, now that is compared to just normal speed. Okay, normal speed, this is what your speedometer says. Tell your neighbor what the answer to this is and why.
I think it's the
Okay, correct answer is B, green. If you're running track and there is no staggered start, do you want to run on the outside or inside lane? Inside. Why? Shorter. Green's running on the outside. There is no staggered start. But green ties with the blue. How's that possible? Green has to run faster. That makes sense? Okay. Here's an equation that ties rotational speed and just normal speed. Okay. This is what your speedometer says. This is how quickly you're spinning. Okay, doing a whole rotation. Good with that? Tell your neighbor.
yes.
Tell them why. Okay. Hopefully this was touched on in the video. Acceleration is the rate at which velocity is changing. What two things do velocity describe? Does velocity describe? Speed and direction. If If you change the speed, that's acceleration. We're down with that. Like that is something we've embraced for a very long time. Okay. If you change direction and not the speed, that is still changing velocity. Okay. If you're not changing the speed, but just changing the direction, we call that type of acceleration centripetal acceleration. Okay. So this is not a totally accurate description, but it kind of gives us an idea. So as you're walking in a circular path, okay, the direction of your velocity at any moment in time is tangent to the circle. So my velocity is going this way at this moment in time, and now it's going this in this direction at that moment in time. How quickly I'm changing my velocity vector towards the center of the circle, we're going to call that centripetal acceleration. It's how quickly I'm changing my direction towards the center of the circle. You know that? So we're not changing the speed, but we are changing the direction. Okay? So Newton's second law says the total force and the net force is equal to mass times acceleration. Okay? If we're moving at a constant speed, but moving in a circular path, this is uniform circular motion, don't worry about that, then the centripetal force is equal to mass times centripetal acceleration. It's the same, see the similarities there? Okay. That force causes acceleration. The centripetal force causes that centripetal acceleration. The direction of acceleration is determined by the direction of the net force. The direction of centripetal acceleration is determined by the direction of centripetal force. Which way is centripetal force pointing? Towards the center. Okay. Good with that? Have a conversation.
Yeah. No, that's the velocity. Oh, yeah. Yeah, mistake. Yeah.
Correct answer is C. Okay. If you hit a patch of ice, what would you do? You would go tangent of the path. What is the force is playing the role of centripetal force? Friction. Which way is friction acting? It's playing the role of centripetal force, pointing towards the center of the circle. Therefore, the acceleration is also towards the center of the circle. Same direction as the force. Good? Okay. All right, so I'm giving you some equations here. Okay, wait for it. Think independently. I will give you a hint. One of these two will give you the answer definitively. One's fuzzy. They're like, but one's like, boom. Know that. Thumbs up when you have a guess. Converse. Tell them why. Yep. Beta. Omega. Lowercase omega. That's capital omega. Yeah. It's Greek. There you go. All right. So, correct answer is? Correct answer is B. Green. Okay. So, here, looking at this equation, the green has a greater speed. As the speed goes up, centripetal acceleration goes up. However, green has a greater radius. So as the radius goes up, centripetal acceleration goes down. You're like, they kind of, I don't know. Now you might argue, well, the speed is squared, so it has a greater influence. It's more impactful on centripetal acceleration. A change in this is going to be a greater effect than a change in the radius, which is true, but you're like, it's still fuzzy. Does that make sense? Like it's not. So let's move over to this guy. Which one has a greater rotational speed? They have the same. Which one has a greater radius? The green. Green has to have a greater centripetal acceleration because they had the same speed, but green had a greater radius. Good with that? You see how we're like, if you can come up with, find an equation that has the same thing for both of them, that's like an anchor point. That's like a, that's going to give me a good conclusion. This is a little bit fuzzy. Okay. All right. How fast can a 400-kilogram car take a non-banked circular entrance ramp that has a radius of curvature of 20 meters before it starts to skid while moving at a constant speed if the coefficient of static friction is 0.54 and the coefficient of kinetic friction is 0.43 between the tires and the road? Yeesh. Okay. So this definitely has some traces of first semester. Okay. So first thing I'm going to do is draw forces. Static. Ooh, is that kinetic or static friction? Okay, we do not want to skid. We want gripping. So it's static. And we want to know like what's How fast can we go before we start skidding? So we're at maximum static friction. Okay. Good with that? Now, problem is we have other forces, but we can't really see them from this vantage point, from this viewpoint. Because gravity is going this way and normal force is going that way. We're seeing them. Okay, so I'm going to draw it in a way that's going to be a little bit more, you don't have to get so artistic, but here's the back of the car, tires, license plate. Good. Okay, so static friction is going this way. You have gravity, normal force. Good? Okay. Always make towards the center of the circle the positive direction. Always make towards the center of the circle the positive direction. So I'm going to make to the right positive x. I'm going to make up positive y. Again, I'm going to ask us the question, do the sum of the forces in the x direction equal to 0? Do the sum of the forces in the y direction equal to 0? Okay. We'll start easier. Let's do the sum of the forces in the y direction. Tell your neighbor, is it equal to 0, yes or no, and why? Do the sum of the forces equal to 0? Yes. Why? Why, though? That is the consequence. How do you know? Because it's at rest in the y direction. It's doing what inertia wants to do in the y direction. So you have normal force minus force of gravity is equal to 0. Okay? In the x direction, do the sum of the forces equal 0? Tell your neighbor, not in terms of the forces, but in terms of the motion, or in terms of, is inertia doing what it wants to do? Is it equal to 0? No. Why not? It's experiencing acceleration. It wants to go in a straight line path, but it's being forced to turn off of that. Okay? So we have static friction is the only thing playing the role, like acting in the x direction. And that's equal to mass times centripetal acceleration. Right with that? Now, often we're going to be substituting in either this equation or this equation for centripetal acceleration. Here we're asked to find how fast it's going. So I'm going to take that and I'm going to stick that in here. That's a lot of the times what we're going to end up doing. So you have maximum static friction is equal to mass times speed squared over the radius. Okay. So I have the mass, I have the radius. Do I have static friction?
Yes.
Got the coefficient. Man, it's more work. That's what that means. So maximum static friction is equal to coefficient times normal force. Shoot. Okay, normal force, that's over here. So normal force is equal to the force of gravity, which is equal to mass times 9.8. Yeah, coming back. Yep, close to 4,000. So you have 400 times 9.8. So normal force is equal to, I think it's 3,920, yes. All right. So we take that, stick that in here. So your maximum static friction is equal to 0.54 times 3,920. Static friction. Gee, I think that's what it was last hour. 2,117. Yes, no, maybe so. 100 times 9.8. Okay. And then we take that. Plop that in there. There it is. Okay. So I'm looking for my speed. Radius of 20. I've got 400. 400 divided by 20 gives me 20. Divided by 2017 divided by 20. 106. Take the square root. 10.3. How are we doing with that? Whole lot of steps. Seems like first semester stuff. I will give you this. This will be the hardest problem of this unit, mathematically. Most involved. Okay? And this will be, this problem right here is going to be the most like first semester for the rest, like this draws stuff from first semester more than any other problem you're going to do the rest of the semester. Does that make sense? I do this unit real fast to tie in last semester. Okay? Good? Questions there? Isn't it crazy? We filled a whole board and you're like, nah, that's not so bad. Well, we made some progress. Learned some stuff. All right, so here's how you bake a circular motion problem. These are the steps I just took you through. The only thing that we did not touch was if I give you period, you got this equation that relates period and speed, or you could go period and rotational speed. Sound good? Got a worksheet due tomorrow. That's the end.